Hello, George Romanic here. Today we are going to talk about Boyle's Law or Boyle-Mariotte's Law. This experimental law is highly related to kinetic theory of gases. But purposely I say experimental because the discovery of this law came before Maxwell, Boltzmann and others put together the kinetic theory of gases. That means people did experiments, and from experiments they concluded the following: that if the temperature in the gas is constant, pressure and volume are inversely proportional. That means if we increase the volume, pressure decreases in the gas. If we decrease the volume, pressure increases in the gas. This law is really important because it can be used to explain many everyday phenomena around us, including breathing, how we breathe. So first, let us see how this law relates to the ideal gas law equation, and then we will discuss some of these phenomena. Boyle's law says that pressure times volume is constant if temperature is constant. This can easily be derived from the equation of state for ideal gas because we know that pressure times volume is number of moles of that gas times R star, ideal gas constant, times absolute temperature. We can see that on the right side, temperature is constant now, R star is universal constant, 8.317 joules per mole per Kelvin, and N is number of moles in this volume that doesn't change. We assume we are not adding or removing gas, which means the right side is completely constant, so we get that PV is equal a constant if temperature is constant. Of course, we can represent this graphically. If we plot volume over here and pressure over here, then the relationship is like this. As we increase volume, pressure needs to decrease for constant temperature to satisfy Boyle-Mariotte's law. Or sometimes people like to represent this in a linear way, but then here you have to plot 1 over P, and then the line gets straight. The most important application, of course, of Boyle's law is to say if we have gas at same temperature, but at two different pressure and volume conditions, then we know that pressure 1 times volume 1 is pressure 2 times volume 2. Boyle's law can be used to explain breathing. How does this law explain the process of breathing? Well, quite simple actually. Our lungs have certain volume. What do we do when we want to inhale air? We expand our lungs. That means we increase the volume of our lungs. Immediately, pressure decreases thanks to Boyle-Mariotte's law. Volume increases, pressure decreases. So, pressure in our lungs becomes lower than the pressure in the atmosphere, and the pressure gradient force says, I will not tolerate this. I want to equalize the pressures, so I will push the air from the atmosphere into the lungs. On the other side, when we want to exhale, what do? We contract our lungs. That means that the volume decreases, pressure rises, and pressure becomes higher than in the environmental atmosphere, and that means the pressure gradient force again tries to equalize the pressures, and the air is pushed out of our lungs. So when you inhale, the volume of your lungs is expanded, but that consequently means that pressure in your lungs decreases, and as I said in my video on pressure gradient force, the moment you have pressure gradient between air inside of your lungs and ambient air, there will be pressure gradient force pushing the air into your lungs. But the initial condition for this to occur was Boyle's law. Similarly, when you exhale, you decrease the volume of your lungs, and that means pressure increases. And pressure increases basically means that pressure in your lungs is somewhat higher than the pressure in the ambient atmosphere. Once again, pressure gradient force takes over and the air is pushed out of your lungs. Another instance where Boyle and Mariotte had something to say about pressures and volumes is related to female flight attendants. Back in the day, stewardesses were required to wear skirts. And they noticed that they would tighten the skirts at the surface, but once they reached the cruising altitude, their skirts would be too tight. In other words, it would seem like they are bulkier. And then some engineers thought about it and figured out that it is related to Boyles-Mariotte's law. Namely, at the cruising altitude, pressure in the cabin is somewhat lower than the pressure at the surface, and we have also air in our body. So as the pressure decreases, volume consequently increases, which means that apparently you become bulkier. And after this was discovered, they introduced a rule that female flight attendants can now have adjustable belts to account for this annoying physics of Boyle-Mariotte's law. Now, if you are constantly at the Earth's surface, you are not flying, you are just at the Earth's surface and you eat a lot, and it happens that you are becoming bulkier and bulkier, that particular phenomena cannot be explained using Boyle-Mariotte's law. Another quintessential application of Boyle's law is in scuba diving. If you take training to become a certified scuba diver, then what they repeat every day, and you have it written everywhere on the equipment for scuba diving, is never hold your breath underwater when you are diving with tanks. Why is that? That's because of Boyle's law, basically. Let us examine this. Here is the surface of the water, 0 meters. Pressure is 1 bar. Here is negative 10 meters, so we are going in depth down. And pressure at 10 meters below the surface is 2 bars. Now we go to negative 20 meters. Pressure is 3 bars. Let's do one more. We go negative 30 meters. Pressure is 4 bars. And so on. Now it is very important to know, if you are scuba diving, that when you are, let's say, at 30 meters, you are breathing air at environmental pressure. That's how regulator on your tank works. So you are breathing air at 4 bars, and your lungs maybe have this size, doesn't matter, for reference. Now, imagine you take air at 4 bars, and you start ascending, you go to 20 meters, and you don't breathe, you keep this air. Well, assuming the temperature is constant, which is good assumption, then as pressure is decreasing, volume of the gas is increasing. So your lungs grow. Now you still don't release your breath, you keep that air, you go to 2 bars to 10 meters below the surface. Pressure decreases, you're keeping that air, which means volume of the lungs will increase even more, and at the surface it would be even bigger. Of course, you wouldn't get all the way to the surface, you would die already from negative 30 to negative 20 probably meters. You might ask, why would you die? Well, let's look at it. Let's just look difference between 0 meters and negative 10 meters, just 10 meter depth. Your lungs, well, at least average male lungs, are about 6 liters in volume. So you take 6 liters of air at 2 bars. This is volume of 6 liters, and now you ascend and you end up at the surface. Without releasing air, you're holding your breath. How many liters will be your lungs at 1 bar? Well, we use Boyle's law. So we say P1V1 is equal P2V2. So this will be my condition 1 and this will be condition 2. So that means 2 bars times 6 liters is equal 1 bar times x liters. And from here, I hope you can see that your lungs will be 2 times 6, 12 liters. And for sure, you will not survive this ascent. What will happen to you is pulmonary barotrauma. That means basically your lungs will explode and you will die. This is very serious business actually, and pulmonary barotrauma can happen already at depth difference of 1.5 to 2 meters. Of course, if you are diving on breath, then this cannot happen, because in that case you are here at the beginning, you take air at 1 bar, okay, you go down, down, and then you come up. But you are coming up with the same pressure that you had in your lungs when you started descending, so it's all good. At the end, let us see one more application of Boyle's law. Here is my now world famous experimental platform. Here is a little bit of water, and here I just have food dye, so we can see what I'm doing. I put a little bit in the water, and now it mixes with the rest of the water. Oh, how beautiful it is mixing. But that's not related to Boyle-Mariotte's law. What is related to Boyle-Mariotte's law is this syringe. Okay, now everything is blue. So, how do we put the water inside of the syringe? Think about it. What you do is you put this into the water, the end of the syringe, and now you take the piston up. And there is water inside. Why? Answer: because of Boyle-Mariotte. What is happening here? What is happening here is the following. This container where the water is now has certain volume. As I am retracting this piston, I am increasing the volume in the container. Consequently, Boyle says pressure will decrease. Pressure will decrease in respect to the environmental pressure. That means when this is in water, environmental pressure in the air is higher than the pressure inside of this container, and there is pressure gradient force acting across the syringe, but it cannot break it apart, but also across the water. So it is pushing the surface of the water down, and then through the opening over here, the water goes in. This is the detailed explanation of how this thing works. But at the end of the day, the backbone is Boyle-Mariotte's law. As I keep retracting this piston, look, I'm adding more and more water into the container. Again, because I'm decreasing pressure into this container, pressure in the atmosphere is unchanged, and there is pressure gradient force acting across this blue water, pushing it into the chamber. But the pressure in the chamber decreased because we increased the volume. Boyle-Mariotte's law. Until next video, goodbye.